Okay, so hello everyone. Thank you for joining the Atto Fridays today. We're going to have the last session of our season of 2022. And this is going to be a hot topic session with early career researchers. And it's a pleasure to have the three of them here. We're going to hear from Xin-Yao Liu, Simon Brennecke, and Antonia Freibert. It's going to be focused mainly on machine learning, but we are also going to have a nice X-ray session. So thank you all for joining and supporting the early career researchers in our field. So our next speaker, and I'm glad she managed to join today, is Antonia Freibert. And she is going to talk. She's actually a former UCL student. She did the master's at UCL, and now she's a PhD student supervised by Niels Huse from Hamburg, Germany, and Oriol Vendrell from Heidelberg. And the topic is going to be quite different, but also quite interesting. She's going to talk about non-adiabatic dynamics of excited molecular systems, and is going to describe X-ray spectroscopy. And I agree, it fits quite well. So the topic is going to be simulating time-resolved X-ray absorption spectroscopy of pyrazine at nitrogen K edge with a full time domain approach. So it has everything to do with the Atto Fridays. We agree with her, and we are happy to have her here giving her talk in the hot topics today. So the floor is yours. Please feel free to start. We're all ears.
Okay. So, can you see my screen?
Yes, is nice.
Okay.
Perfect.
Okay, great. Yeah, many thanks for the kind introduction. And yeah, first of all, thanks to all organizers for giving me the opportunity to present my work today. So yeah, as already mentioned, I'm going to talk about simulating time-resolved X-ray absorption spectroscopy of pyrazine at the nitrogen K edge with a full time domain approach. During the past 2 decades, experimental developments of ultra-fast and intense X-ray sources made it possible to extend pump probe techniques into the X-ray domain. And this allows tracking photo-induced molecular processes by core-level probing with femtosecond time resolution, or even in the attosecond time regime. However, due to the complex nature of the underlying processes, we usually rely on computer simulations to support experimental measurements and to extract the right information from the data. And yeah, for an accurate description, we need to solve the time-dependent Schrödinger equation. But as we all know, for almost all chemical systems, it is impossible to find an analytical solution. Hence, several assumptions and approximations must be made to implement a workable method. And in this talk, I'm going to discuss 2 widely used approximations when simulating X-ray spectroscopy, namely the short time or Lorentzian limit approximation, which states that the nuclear dynamics after X-ray probing is insignificant. And further, we discuss how an explicit description of the external electric field might influence the outcoming spectra. Let's start with a little bit of theory to understand where it comes from. So when we are interested in simulating equilibrium ground state X-ray absorption spectroscopy, we can apply Fermi's golden rule to calculate the static absorption spectra. So in a bit more detail, Fermi's golden rule states that the transition probability from an energy eigenstate, here denoted by psi naught, to a final excited state psi j, is given by the overlap of the corresponding wave functions. So the peak intensity for a specific transition is just defined by this matrix overlap element. And since for example, the lifetime of the core states are very short, we also get a spectral broadening controlled by this dephasing factor gamma. Alternatively to this energy domain approach, we can also use wave packet dynamics for simulating absorption spectrum. So yeah, in the completely equivalent time domain approach, what we are doing is we put our initial wave function onto an excited state where there's no eigenfunction anymore, but a wave packet and let it evolve. And the absorption spectrum is then given by the Fourier transformation of the autocorrelation function of this wave packet. However, the situation becomes more challenging when starting from a transition state, and the theory behind must be adjusted. But yeah, as my title suggests, this is exactly what we are aiming to do. So we want to simulate time-resolved X-ray experiments to get a better understanding of the photo-induced molecular processes. That means the situation we now want to describe is that we have an optical pump pulse that brings our system into an excited state and triggers the photochemical dynamics we are interested in. And then we probe that photochemistry by sending a second X-ray pulse at different time delays, which allows us to observe the photo-induced dynamics from the perspective of a specific atom in the molecule. Yeah, in contrast to before, where we started from the equilibrium ground state, we now have this evolving wave packet triggered by the first pump pulse, and we want to calculate the transient X-ray absorption spectrum. So in particular, we now must take into account not only the dynamics on the final electronic state, but also on the initial state, since it isn't stationary anymore. And thus we get our transient X-ray absorption spectrum by the Fourier transformation of the dipole-dipole correlation function, where now both the bar and the ket are time dependent. Yeah, to make life a little bit easier, the short-time approximation we want to discuss states that due to the very short-living nature of core excited states, the wave packet evolution is insignificant during the transition. So mathematically spoken, it states that the transition dipole operator and propagator commute. And if we substitute this condition into our expression for the full dynamical dipole-dipole correlation function, we end up with a correlation function where the kinetic energy operator is cancelled out. So in other words, the short-time approximation completely neglects any dynamics after X-ray interrogation, and we can find this equivalent expression for the energy domain. And since so far most theoretical studies of time-resolved X-ray absorption spectroscopy are done within the Lorentzian limit, we wanted to know how good this approximation really works, or rather what we are actually missing when applying it. And for this purpose, we set up a Hamiltonian containing all relevant states and performed two sets of calculations. One using the full dynamical approach, and one where we deleted the kinetic energy operator after X-ray interaction, while all the rest remains the same. So in particular, with this, we've got a clear comparison of the two approaches without having any further approximations. And for this, we needed a test system, which was pyrazine. And yeah, pyrazine is a typical benchmark system for such kind of theoretical studies, since it has an interesting UV photochemical behavior with several conical intersections between the valence excited states, but it is also a relatively small, highly symmetrical molecule, which makes it easier to handle. And yeah, its UV induced dynamics is already well described by several theoretical models. So we actually know what we in principle have to expect and can hence validate our model for the study. And in our calculations, we assumed a core hole lifetime of 8 femtoseconds, which is consistent with experimental measurements at the KEH of molecular nitrogen. Yeah, as mentioned, we want to calculate our spectra within a full time domain approach using wave packet dynamics. And for the nuclear dynamics simulations, we used the MCTDH method, which is a grid-based full quantum mechanical method counting as the golden standard under quantum dynamics simulations. And this method requires pre-calculated electronic states. So we firstly set up a molecular Hamiltonian where we assumed that the valence and core excited state manifolds are completely decoupled, which is justified by the huge energy difference between them. For the valence excited states, we used an already existing validated model and extended this with 3 more core excited states. And for the core excited states, we used the linear vibronic coupling approach to approximate the Hamiltonian, yielding a very good fit, as you can see, for example, here along one of the symmetric vibrational normal modes. So yeah, okay, let's come to some results. Yeah, before we look at actual spectra, it is worth to consider the valence excited state population, which is strongly connected to the photochemical dynamics we want to track. So here, what we see is that so the yellow S3 state was initially populated through an instantaneous vertical excitation at time 0. And then the population of S3 rapidly decays into both the red S2 state and the green S1 state, which can be explained by low-lying conic intersections between both pairs of states. And after approximately 55 femtoseconds, S3 is almost depopulated, but the population dynamics between S1 and S2 keeps oscillating with a period of approximately 65 femtoseconds. And indeed, this population dynamics is accurately mapped by the transient X-ray absorption spectra, which are shown here for time delays of 0, 20, 35, and 55 femtoseconds. So the contributions of the transitions from each valence excited state are here highlighted by the same color as used in the figure for the state population. So what do we see? Obviously, immediately after the pump excitation, only the excitation band starting from S3 can be seen. And after 20 femtoseconds, the population is almost equally distributed over the 3 states, and contributions of all 3 transitions can be seen in the spectrum. Moreover, for the green S1 state, the population reaches its maximum at about 35 femtoseconds, and for the red S2 state at about 55 femtoseconds. And this is exactly what we see in the corresponding spectra on the right-hand side. So we have this band maximum for the green S1 state at 35 femtoseconds and for the red S2 state at 55 femtoseconds. These spectra were calculated including any dynamics, but now we can also see the resulting spectra within the Lorentzian limit shown by the red curve. So the overall shape of the absorption bands within the Lorentzian limits is in good agreement with the full time-dependent calculations. And generally, the excitation bands have a rather broad and asymmetrical shape for both approaches, which must be hence traced back to the evolution of the nuclear wave packets on the valence excited states. However, as we have seen before, the coherent wave packet dynamics after probe excitation in both the valence and core excited state manifold is only covered by the fully time-dependent approach, whereas the Lorentzian limit approximation is only sensitive to the probability distribution of the valence states wave packet. And this is why the spectra within the Lorentzian limit lack finer vibronic structure, as we can, for example, see here in both dominant absorption bands for a time delay of 20 femtoseconds. So now I want to come to the second part of my talk and discuss the influence of the external electric field, and why we needed delta pulses for a clear comparison between the Lorentzian limit and the full dynamical approach. We now want to go beyond this picture and include an explicit description of the external electric field. For this, we treat the electromagnetic field as Gaussian-shaped laser pulses and used a non-perturbative approach to calculate our spectra. And one can show that the spectrum is proportional to a response function, which in turn is defined by the product of the Fourier transformation of the expectation value of the transition dipole operator and the Fourier transformation of the electric field. Now we can see the effect of a finite pump pulse duration on the X-ray probe response. So along the rows, we increased the pump pulse duration from approximately 1 femtosecond to approximately 80 femtoseconds. And for each row, we show the valence excited state population dynamics, the linear UV absorption spectrum, and transient X-ray absorption spectra for 4 different time delays. And yeah, in the pyrazine system, we have this oscillatory behavior between S1 and S2, as I mentioned earlier. And as you can see, for pulses shorter than 20 femtoseconds, the 2 dominant absorption bands reproduce this very well. So we see this up and down of the 2 dominant bands. However, since the excitation process lasts for the entire pulse duration, longer pulses might lead to blurring effects. And yeah, for pump pulses longer than 50 femtoseconds, it becomes nearly impossible to extract relevant information about the underlying dynamics, and the transient absorption spectra seem to be nearly time independent, as we can see in the last row here. Yeah, so far I restricted my analysis to excited state transitions only, but of course in real pump probe experiments, we can't neglect contributions from the ground state. So this is why I finally show the calculated differential absorption spectra as we would get them from experiments, where the positive contributions stem from the excited state absorption and the negative signals are due to the ground state bleach. Yeah, for pyrazine, we see that the X-ray transition from the ground state is much more likely than from the excited states, leading to a very dominant negative bleach signal. However, this dominant bleach signal doesn't overlap with the time-dependent signals, and we can thus still see this typical oscillating behavior of the 2 dominant excited state absorption bands. So to summarize my main part, we have seen the power of the full time domain approach, as it can avoid the short time approximation without having more effort, as well as include an explicit description of the external electromagnetic field, which is needed to accurately reproduce the situation in the lab. While we have seen that the Lorentzian limit works okay for time-resolved absorption spectroscopy, it might cause larger errors when simulating RIGS experiments, as here the core excited states are immediate states and the valence excited states are the final one. Sorry. So yeah, so an ongoing project is actually to extend the full time domain approach to RIGS simulations. And yeah, as there are a few minutes left, I want to now give a brief overview of how to simulate RIGS experiments using wave packet dynamics. And I will also shortly discuss the advantages of a full time-dependent approach. So in general, resonant inelastic X-ray scattering is a coherent scattering process where the system is firstly excited by a X-ray photon onto the short-lived core-excited state manifold, and then it continuously decays into the valence excited states as well as back to the ground state. Hence, we will later see that our RIGS cross-section is dependent on two frequencies, namely the incoming photon frequency, omega, and the scattering frequency, omega prime. And yeah, RIGS complements absorption spectroscopy methods, as for example, one might reach valence excited states which are not directly accessible in the UV range. And also in RIGS, the spectral resolution is not limited by the large core lifetime broadening as it is in X-ray absorption spectroscopy. And hence RIGS can also deliver information on the nuclear motion through vibrational substructure of electronic transitions. And the conventional approach for calculating RIGS experiments is cast in the energy rather than the time domain. So generally the RIGS cross-section is, as already mentioned, dependent on both the incoming and scattering photon, and it is proportional to the squared polarizability. In the energy domain, the polarizability is given by Kramers-Heisenberg formula, where 0 denotes the ground state, I is the intermediate core excited states, and F is the final ground or valence excited states. So as before, for absorption spectroscopy, we can derive an equivalent time-dependent expression. And in the time domain, the polarizability is given by the Fourier transformation of the autocorrelation function of the so-called Raman wave function. So the Raman wave function is independent of time and can be understood as the state from which the emission takes place. That means if we compare the two photon RIGS process with the one photon absorption process, the Raman wave packet just replaced the initial wave packet when calculating the spectra. In RIGS experiments, the effective lifetime on the core excited state manifold can be controlled by detuning the excitation from resonance. So in a bit more detail, there's a reciprocal relationship between the time interval that contributes to the Raman wave function and the detuning delta omega. And hence detuning may serve as kind of a molecular clock as it controls the time interval of the dynamics. And these effects can be clearly explained by the nature of the Raman wave function, which also means that the Raman wave function is not only a mathematical construct, but it has indeed interesting physical interpretations. So there's one last thing I want to point out before I finish my talk, namely both Kramers-Heisenberg formula and the Raman wave function approach are only valid if you consider a continuous wave experiment. So if you really have a monochromatic wave. But of course, that's not the case in real experiments. And but by using a full time-dependent approach, we can easily include a proper description of the external electric field, as I have already shown for transient X-ray absorption spectroscopy. And by including this proper description of the field, we can then study effects that stem from a finite pulse duration, and we may also figure out how long a pulse must be to count as a continuous wave, which in turn might be important for future experiments. Furthermore, there's a substantial interest to apply RIGS in pan-probe spectroscopy. And with a full time domain approach, we should be able to extend our method to time-resolved RIGS, like we did for XAS, by including any dynamics on the core as well as on the valence excited state manifold. And last but not least, using wave packet dynamics with an explicit description of the external field will also allow us to explore stimulated X-ray emission processes as accurate as possible. And I hope there will be some results on pyrazine very soon. But for now, I want to leave it as an outlook. And before I eventually finish my talk, I want to thank both groups in Hamburg and Heidelberg and special thanks goes to David and my supervisors Niels and Oriol. And of course, thank you for listening.
Well, thank you so much for your talk. Are there questions, comments? Do feel free to write in the Q&A tab or raise your hand if you wish. And we're looking forward to your talk, to your questions. People are quiet sometimes. No? Yeah, people are quiet. But I mean, you mentioned that there is a difference between RICS and the standard spectroscopy that you were discussing before, and you said that there were transitions that were not accessible that you would like to have a look at. Could you be more specific?
Yeah, of course. So for example, in pyrazine, here are some surfaces. So the two low-lying core-excited states are almost degenerate. So I mean, in this figure, we just see one, but there are actually two. And we see non-adiabatic transitions even in this very short core hole lifetime. And yeah, this allows different transitions. I mean, if we just have a transition to one state, it will go back to valence excited state, which would be or probably also reachable by directly from the ground state, but by having this non-adiabatic transitions to a state of different symmetry, we will also get transitions which are allowed by the symmetry rules, which would be forbidden directly from the ground state. So this is one example where how we could reach valence excited states that are not directly accessible from the ground state.
Okay, and this allows then tracing the dynamics.
Mm-hmm.
Very good. Okay, thank you so much. Are there questions, comments? Come on. I'm grilling everybody here. Nobody asks anything. So for those who are watching on YouTube, and there were quite a few of you today, take good care of yourselves. Have a great Christmas, New Year, holidays, relax, and we will be back in late January. So take good care of yourselves. If you would like to ask questions, but you're a bit shy, just hang in there because you have the chance, and see you soon. Thank you for joining and supporting our early career researchers.